This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 2 weeks. Thanks to our audience and the partners listed on our website for supporting the podcast. Welcome, listeners, to another episode of Software Engineering Radio. This one is another language episode. It's not necessarily about a new language, but it's about a bunch of new features for a new version of that language. It's about C++ OX, or whatever the correct pronunciation is. Our guest today is Scott Meyers. And, hi, Scott.
Good morning.
Hello. Why don't you introduce yourself to our listeners so they know who you are? Maybe they already know because you've written a couple of books, but who knows?
All righty. I am Scott Meyers, and I've been working with C++ for a distressingly long time. I think it's over 20 years at this point. Mm-hmm. And I've written some books on using C++, and I do consulting and training on C++. And compared to many other people, I'm not a multiple language guy. I'm really pretty much focused on C++. I have some other interests in terms of software quality and high performance programming, but it usually ends up coming back to C++.
Mm-hmm. I always found it interesting that C++ is one of the languages that where people can make a living being a consultant about the language. For example, for Java, that's not the case. You have to be some Java Enterprise Framework person or whatever, but you can't make a living from the language itself. I wonder if this is a good or a bad sign for the language.
Let me put it this way. I think it is indicative of the complexity of the language.
Yes.
My view of all programming languages, including C++, is that effectively they are tools to help programmers get a job done. And essentially, C++ is a very large, very complicated, very powerful tool. And my job in many cases is to help people understand how they can make the best use of that tool in solving whatever problems they want to solve.
Yeah. Okay, so C++ OX is the new standard. Is it already finalized?
No, it's not finished. In fact, about a week ago, they came out with what's called the final committee draft, which essentially says we now know everything that's going to be in the language. We've nailed down most of the details of what the new revised standard is going to look like, but there's still a few things to work out. At this point, the expectation, or at least the hope, I guess, is that it'll be finished officially in 2011.
Okay.
But practically speaking, for programmers who want to know what the new version is going to look like, they now know what it's going to look like. And more importantly, for compiler and library vendors who want to know basically what the language is going to look like, they also have something they can start implementing.
Yeah. And the OX, is it a hint at hexadecimal, or is it does it mean 2000 and something with the idea of being only one digit at the end of the something? I mean, is it intended to be the 2000 something standard?
Well, it's a sign of youthful idealism. The original hope was that it would be finished by 2009, and obviously they did not achieve 2009. So officially, it's going to, at this point, be done in either 2011 or possibly 2012.
Okay.
But there have been a lot of jokes about how X is going to be a hex digit. I was really sort of hoping that they would finish in 2010, because then we could have said that X was the Roman numeral.
Yeah.
So we didn't achieve that, unfortunately.
Okay, and so why has it been started? I mean, although there is no hype anymore around C++, at least not in the circles that I deal with, I guess C++ is still a relevant language, and there was a reason to do a revision on it, right? I mean, there was need to improve it.
Well, the original standard for C++ was effectively finished in 1997, and it was officially standardized in 1998. So we're well over a decade past that. And, in the past decade, if you think about all the kinds of changes that have occurred in computing, most notably things like multi-core development and stuff like that, but also just the rise of the web and lots of other things, the way in which you use programming languages in general has really changed in the past decade. And it became very clear, even in 5 years after the standard, that they were going to have to start making some changes to it. And so originally the Standardization Committee put a lot of attention on addressing how to augment the standard libraries. There'd be more library facilities. Mm-hmm. And so in 2005, they came out with something called TR1, which stands for Technical Report 1, and it is essentially a list of 14 fairly substantial new kinds of functionality added to the standard library. And however, even at that point, C++ did not officially have something that supported, for example, concurrency.
Mm-hmm.
So if nothing else, it was very obvious that the language was going to have to be updated to at least officially acknowledge the existence of parallelism.
Yeah. Yeah, I guess that has always been, maybe it's too much to call it a problem, but I mean, we know from the Java and the .NET worlds that the libraries are standardized and they contain a lot of stuff. So basically everything you really need every day is standardized. And that hasn't been the case for C++. And concurrency is one aspect of that.
Yeah, concurrency is one aspect. C++ is sort of interesting in that it's really gone off in its own way in a couple of areas. And if you look at, for example, Java or C# as sort of the two obvious examples, they have these very, very extensive collections of standard libraries. And so I think that for people who are writing programs in those languages, and I'm not experts in those languages by any means,
Yep.
but a lot of the work consists of identifying which standard components will mostly get you where you want to go and then figuring out how to make them talk to one another.
Yes, I agree.
And C++ has a comparatively impoverished standard library. As a result, people write a lot more code from scratch. On the other hand, C++ has put a lot of work into things like generic programming, the template-based stuff, which has, as I said, taken off kind of in a different direction. And a lot of that shows in C++ OX.
Yeah. Okay, so let's take a somewhat closer look at OX. Is there any general direction that you can identify? Maybe, well, obviously, in addition to concurrency, is there a kind of coherent story to the C++ OX, or is it a set of kind of independent, additions?
I'll tell you the truth. It's interesting, and I should mention right now, I am not on the standardization committee, and I have never been on the standardization committee. So I sort of sit and look at C++ to some degree as an outsider. And about a year ago, when I first sat down and said, well, it looks like C++ OX is now getting to the point where people can start to use it, so let me sit down and sort of familiarize myself with this newer version of the language.
Yep.
And I thought, it's going to be kind of an update. This is an enormous change to the language. The new standard is going to be twice as big almost as the old standard.
Mm-hmm.
So in addition to adding fairly important things like support for concurrency and a lot of different kinds of support for generalization, there's also goodies that make programs just a lot easier to write in general. There's ways of unifying the syntax. So when I sat down to try to figure out how to make sense of C++ OX, I broke it into 3 parts. And one of the parts was what I call features for everybody, which is just useful if you're writing any kind of C++ program.
Mm-hmm.
And then a collection of features that I call features for class authors, which are additional features which make it easier to write classes. And then there's a third set of features which I call features for library authors. So there's not one consistent story because there's a lot of different things going on simultaneously. It's a very substantial upgrade to the language.
Okay. So I guess that will make sure that you'll have enough work to do with a big and complex language for the next 10, 15 years.
I think that there is adequate ground there, yes.
Okay. So, well, obviously we can't cover every little detail and every addition, and obviously only to, a certain depth. But we have identified, actually, you have identified a bunch of important the main additions of the new standard, and we're basically going to walk through them, and you'll try to explain to me what it means, and then we'll hope that the rest of the audience, if I understand it, they understand it. That's the idea.
Okay, fair enough.
Okay, so I guess let's get started with concurrency. It's obviously the big story that everybody really needs to know how to do it in C++. What's going on there?
What's interesting about the concurrency stuff is that you can sort of start at a very high level or you can start at a very low level. And so just for kicks, I guess I'm going to start at the high level and work my way down from there. So the first thing is, from a programmer's perspective, you get to assume that the language actually knows what concurrency is, which doesn't sound terribly interesting, but it provides you with a lot of guarantees you might not otherwise have. So, for example, C++ has static objects, which can be global objects or they can be inside classes or whatever, and they have to be initialized exactly once. And so one of the things that C++ now will guarantee you is that those things are going to be initialized in a thread-safe manner, which you should be able to take for granted, but in the past you have not been able to take that for granted. So So that basically things just naturally work that you should be able to expect would work. But in the past, again, there was no guarantee. If you want to, for example, just spawn off a new task, say I want to run this thing asynchronously and just have it run, there was a really easy way to do that. There's a library call now called async, and you simply say, this is what I want to run asynchronously, and these are the arguments that you pass to it. But what I did want to mention about async, because it represents in some ways some of these ideas I mentioned before about generalization, is that when you call async, conceptually what you say is, here's a function I want you to run, and here's some arguments that I would like you to pass to that argument, to that function when it runs.
Mm-hmm.
However, you don't have to pass a function. It turns out you can pass anything that is callable. So it's what we call function objects in C++.
Mm-hmm.
So it can be a function, it can be a function pointer, it can be a function object, it could be a bound member function. Basically anything that is executable is something which now can be run remotely, and they're all treated the same way.
Okay, you said remotely or asynchronously?
I'm sorry, asynchronously,
okay,
excuse me.
I thought there was even more magic to it.
No, my mistake, asynchronously.
Okay.
And then the second thing which is kind of interesting about that is I said you then pass a set of arguments. And it turns out that you can pass whatever arguments you want of whatever types you want, and you can pass as many of them as you want. And those will all be passed automatically in a type-safe manner.
So how would I have to imagine the syntax for that? I mean, if I can pass in all kinds of things, there needs to be some kind of unified syntax for doing that. Do I just write like a method call and put the async keyword around it, or how do I do it?
You essentially, you say async, which is a non-member function call,
mm-hmm.
and then you give the name of whatever you want to execute. So it'll be a function pointer or a function object, whatever it happens to be.
Yep.
And then you just have a comma-separated list of parameters.
Okay, I see. Mm-hmm.
And so it's very, very simple from a user's perspective, and automatically the whole issue of firing up a new thread and getting it running on a new thread and doing all the type-safe passing of arguments, all that kind of stuff, managing the lifetime of those arguments to make sure that they exist long enough
mm-hmm.
for the function to execute it, all that stuff is handled automatically.
Okay.
So that's async. Now, so that's at the highest level, and just for kicks, I'll jump now down to the very lowest level.
Mm-hmm.
At the very lowest level, there are a whole collection of atomic data types that allow you to do manipulations on data types with the assumption there's going to be an atomic operation.
Mm-hmm.
The lowest level of those things are going to presumably map to machine hardware. So if you have, let's say, an atomic int or an atomic boolean, something like that, you should reasonably be able to assume that that's going to map to a machine instruction, assuming there is a machine instruction which does the right thing.
Mm-hmm.
This, however, has also been generalized so that there's a template for atomics, and it turns out that if you happened to need a specific kind of atomic that the machine doesn't support, so maybe it's a 64-bit integer or something like that, you can use the same syntax for that, and the underlying library will automatically implement that for you, probably by creating a mutex to lock and unlock that so you get atomic operations.
Can I also do this for complex like structs or something, or whole?
You can do it anything that you want to.
Okay.
You can. It basically is because it's a template. It'll take any data to support certain operations.
Sounds a little bit like transactional memory.
I don't think it's like transactional memory in the sense that there's no such thing as an abort, for example. It's more a matter of, this is a set of operations I want to execute with mutual exclusion.
Yeah.
But for example, if an exception were to be thrown in the middle of that, then you would release the mutual exclusion, but that you're not going to undo anything that had already been done at that point.
I see. Okay.
So it's not transactional memory.
And can I also modify several independent data structures? Is there some kind of bracket I can put around something, or do I have to do that with mutexes then, with low-level programming?
You typically would do that with mutexes.
Okay.
The idea behind atomics is that, for example, if you wanted to write a lock-free algorithm, then the idea is that an atomic, in theory, will give you that, assuming that the machine gives you the atomics that you want.
Yeah.
But because so much programming in C++ is done with templates, which means you don't know the exact type that you are dealing with, it's very important to be able to just sort of say, I'm going to assume that T is atomic, although I don't exactly know what T is, and I'm going to manipulate it using the atomic interface.
Okay. Mm-hmm.
And then the other thing I wanted to mention, which is different, I think, from other programming languages, at least the ones that I've heard of, is the underlying hardware will often have what are known as relaxed memory models. And
What's that?
Relaxed memory models means that the hardware gets to reorder the loads and stores in terms of what's happening in the underlying machine. So, for example, in your program, you might say, I'm going to set X I'm going to say X gets Y, and then I'm going to say, A gets B. And that's what you write in your program. And it's possible that the machine actually executes X gets Y first and A gets B second. However, the underlying hardware, unless it is constrained on some machines, may decide that it's actually going to do the load to A first, the store to A first, and the store to X second. In other words, it may reorder these loads or reorder these stores. And this can turn out to be an important capability for certain kinds of fairly specialized programming. Okay. And in C++, by default, you get what's known as program order, which means things behave the way that a sane human being expects them to behave.
Yep.
However, if it turns out that you know certain kinds of, for example, if you know that X and A are completely independent, which means that it doesn't matter what order they actually get written in, then you'd like to give the underlying hardware permission to do those kinds of reorderings, because in some cases that can yield a performance improvement. Mm-hmm. And so the underlying atomics actually allows certain kinds of, I'm going to call them attributes, but that's not quite the right word, that allow you to specify to the underlying compiler code exactly what kind of reorderings are permitted or are not permitted. Mm-hmm. And I think this is very much in line with the traditional notion of using C and C++ for very specific high-performance work, is you still have a lot of control over what goes on.
Yeah.
So that's the high-level stuff for concurrency, and the low-level stuff for concurrency, and in between, there's a whole bunch of stuff. There's mutexes that we mentioned in passing. There's condition variables that we mentioned in passing. It's got support for timeouts. It's got support for what are known as promises and futures, which essentially is a communications channel between an asynchronous thread of execution, so you can talk back and forth between a caller and a callee. There's a way of bundling those together in certain convenient manners called a packaged task.
Mm-hmm. I think I know what a future is, and I guess most people know it. It's basically a return value which you can later query for the actual return value once it's asynchronously provided. What is a promise?
A promise is the other. Let me put it this way: a future is what a caller gets.
Yes.
So you spawn an asynchronous thread of execution, and then you wait for the answer, and what you get back is a future.
Yep.
A promise is what is used by the callee to deposit the return value into the future. So the promise, in some sense, is okay. How you get a value into a future.
Yeah, it's the other end of the wormhole.
The other end of the pipe.
Yep.
And it turns out that you may, for example, you might decide that what you want to do is have 3 different threads, all which are trying to compute some answer for you in a different way. And whichever one does it first gets to give the solution to the future.
Okay.
So that's one of the things that it lets you do.
Okay, cool. Sounds good. Okay. So anything else in the concurrency space? I see that there is, everybody else talks about functional programming and immutable data structures and message passing because shared memory is evil. At least some people say that. There is no such revolutionary change to the C++ language in that.
No, there is no such revolutionary change. The people in the committee certainly took a look at that, and I think what they decided was that in keeping with the philosophy of being able to do very, very low-level stuff, they wanted to give you the building blocks to build whatever you wanted to. Yeah. For example, unfortunately in C++OX, there isn't even something like a thread pool.
Okay.
However, there are the underlying building blocks so you can build all that kind of stuff. So essentially, C++OX puts the foundation in place for building higher level abstractions. And if you later decide you want to have a message passing architecture or whatever, that's great. You can build it on top of this.
Yeah. And since you mentioned thread pools, can I plug in a thread pool into the async facility so that the async doesn't start new threads all the time, but rather uses a thread pool that I provided with certain policies and characteristics?
There's no way to specifically plug that in. Now, what you could do is you could write your own implementation of async. I do that, but effectively, async is part of the standard library.
Okay.
So you are going to be, at the mercy of your standard library implementer.
But they could provide a kind of interface with which I can configure the implementation of the standard library, which would then be vendor specific or something.
Exactly. They could give you that kind of an extension if they wanted to.
Mm-hmm. Okay, so I guess let's move on to the next topic. They are, by the way, in no particular order. And the next one I wrote down is autotype or autotyping. Implicitly typed variables are also known as type inference, right?
I guess you call the process is type inference. Auto is, in my opinion, going to be the thing that most programmers will notice most quickly and will fall in love with the fastest.
Okay.
Because what it means is that you no longer have to specify the type of a variable as long as that variable is given an initialization value. Mm-hmm. So basically, instead of saying something like, vector of int : const iterator I equals some expression, which is something you have had to write in the past, you'll just be able to say auto I equals that expression, and it automatically will have the correct type.
Yeah, and that's, of course, not just, well, if you think about ints and shorts, then this is not a very interesting feature because the word int is shorter than the word auto. Yes. But if you consider, complex templated types, then, of course, this is very convenient.
Yes, it will be very nice. And the other nice thing about it, too, is it also means that if, for example, you make some changes to your code so that the types that are being returned from functions maybe change a little bit, then you don't have to go back and change any of those type declarations. Instead, auto automatically updates things to be the new type. Yeah. And I want to emphasize that everything is still completely statically type checked. Yeah. So this is not a dynamic language. This is the compiler essentially figures out what the type is, but you still can't make type errors in your programs any more than you would be able to using your own types.
Yeah. And where does this work? You mentioned, I think, kind of a local variable declaration. Does it also work for parameters? Like I probably can't work there.
It doesn't work. It doesn't work for parameters. But if you think about it, templates already give you that capability with parameters. If what you want to say is I have a function that will take any type of parameter, you just write a template and you say it takes type T. Mm-hmm. Yep. So this is the capability that the language has always had for functions. So the parameter problem was never there. Yep. However, what this means now is that any variable, whether it's a global variable or a local variable, pretty much any variable, because member variables actually you still have to give a type to. But normally, if you are declaring a variable and you give it an initializing expression, then you can use auto. Mm-hmm. Cool. On the other hand, if you just say, you can't just say auto I. Because now there's no initializing expression. Can't figure it out. Unless you write auto with a capital A and it's actually a class name. Haha. That you could do.
Okay. Mm-hmm. Yeah, I guess that's...
I think you've got a C++ programmer deep down inside you somewhere.
No. Well, I did some C++ programming a long time ago, but I never got paid for it. So I never did it for real.
Okay.
I do deal quite a bit with C these days in embedded systems, but without the ++.
Embedded systems, in my mind, is one of the places where C++ is likely to be more important than it has been in the past. I see a lot of use of C++ in embedded systems, especially in things like video games, automotive, but just embedded systems in general.
Yeah. What I also see quite a bit is that people kind of go directly from C to domain-specific languages in code generation and consider the C more or less as something that's generated anyway, so they don't even bother going to the C++ part. Not everywhere, but that's what I also see in quite a bunch of places.
Interesting.
Yeah. Okay, next topic that I wrote down here is R-value references. No idea what this could mean.
Yeah, and really, rather than talking, let me put it this way. There are two high-level goals that C++ OX wanted to be able to offer to people. And the most important one, in my opinion, is what's known as move semantics. Mm-hmm. Now, C and C++ are both value-oriented languages. And the idea is that if I say, for example, that X gets Y, that after that, X and Y have their own separate chunks of memory, and X and Y are completely independent. Okay. So unlike languages like Java and C#, which have reference semantics, where if you assign one object to another, you're really just assigning a reference.
Although I can emulate that by using a reference, like the ampersand facility, to have two variables pointing to the same thing.
But the point there is that you, under those conditions in C++, you actually have a pointer.
Yes. Okay, I see.
But the point is the language itself expressly has pointers, and so you can get reference semantics in C++ if you want to.
Mm-hmm.
But if you just have an object and you say, I want to copy this object, you are going to get a completely different copy of that object.
Right.
And in fact, this rule also applies to pointers. Essentially, if you have a pointer and you copy it, you get another copy of that pointer.
Yes.
So the rule is completely uniform.
Mm-hmm.
And this is nice in many ways. Unfortunately, it leads to certain kinds of inefficiencies. So as an example, if you have, let's say, a function which returns a heavyweight object, so maybe it returns a matrix or something like that, the normal rule in C++ says that you're going to make a complete copy of that matrix that gets returned from the function.
Mm-hmm.
And sometimes this is what you want, and that's correct. And other times, it gives you correct behavior, but it's very inefficient.
Yep.
So the idea behind move semantics in C++ OX is to allow the compiler to be able to detect for any arbitrary type, including user-defined types, when it is not necessary to make a copy, and instead you can simply move the contents of one object into the contents of another object.
Mm-hmm.
So this is the idea behind move semantics. It essentially says, I'm going to give the compiler enough information so that it will be able to figure out when it doesn't need to make a copy, even for user-defined types when it doesn't know what the type means.
Mm-hmm.
So that's the idea behind move semantics. It's an efficiency improvement. And what you mentioned actually were R-value references. And it turns out that R-value references are a new special kind of reference in C++ OX that make it possible to seamlessly implement move semantics.
Mm-hmm. So what do I have to do as a programmer to tell the compiler that in certain places move semantics is valid, is possible? Or
this is the real sweet thing. You don't have to do anything. And in fact, one of the things that's really nice about move semantics is if you have a program which is valid C++ right now,
mm-hmm.
and you simply get yourself a C++ OX compiler, which comes with a C++ OX library, all you have to do is recompile. And magically, inside your program, places where you were unnecessarily making copies will start doing moves instead. It will not change the behavior of your program, but it should improve the efficiency of the program.
Mm-hmm.
Now, on the other hand, the idea behind move semantics says, I have an object and I can move its data from one object to another. I don't need to copy the data, I can move it.
Mm-hmm.
And this is especially important, for example, if you have a pointer to a data structure on the heap.
Yeah.
And what you want to do is just copy the pointer rather than copying everything on the heap.
Yeah. Deck is, of course, different.
Well, it actually, if you think about something like a string, strings usually have their data on the heap.
Yeah. Mm-hmm.
So the thing is, so to copy a string in C++ usually means you copy the data on the heap as well.
Yeah.
Because remember, after the copy, you need two completely independent objects.
Mm-hmm.
But in some cases, with move semantics, the compiler can figure out that there is, in fact, no need to make the copy.
Okay.
And as a result, you can just move the pointer instead, which is much more efficient.
Sure. Yeah.
And what users do need to be able to do is for an arbitrary type. So if I've come up with my own special type with its own special data structures, I do need to have a way to specify to the compiler, if you decide that you want to move this data from one object to another, how do you do that move?
Mm-hmm.
Now in C++, we've always had what's called a copy constructor.
Yeah. Mm-hmm.
How do you make a copy of this thing?
Mm-hmm.
So in C++ OX, we now have what are known as move constructors, which allows you to say, if you want to do a move, this is how you do it for this type.
Okay.
So getting back to your comment originally or actually your question about R-value references are the underlying language feature that makes it possible to implement move semantics. But in my mind, for most programmers, the actual feature they're going to care about is move semantics and not R-value references.
Right. And for a typical user-defined type, like a class with a bunch of, member fields, what is it called in C++? Mm-hmm. Attributes, fields, members?
Data members,
okay. Do I typically have to implement a move constructor, or is the default behavior good enough for most cases?
It's interesting that you should ask that, because 2 weeks ago, I would have said that you have to implement move constructors yourself regardless because they're not generated by the compiler. But since it's now 2 weeks later and there has been another standardization meeting, one of the last things that they did before voting out this final committee draft was to add the conditions under which move constructors will automatically be generated.
Okay.
And so for most types, I think it is reasonable to assume that the compiler will be able to generate a move constructor for you automatically.
Cool.
And if it turns out that that's not exactly what you would want, then of course you can change the behavior yourself.
Yeah. Oh, this sounds really interesting. And it's kind of, as you said before, C++ is a language for kind of low-level and efficiency-oriented programs, and this is another step in this direction.
Yeah, it's also the language, to be honest. I mean, it's for efficiency, but it's also for control. And so, sort of the goal is to have the language do something for you, probably with great efficiency, but if you don't like what it's doing, give you the controls and the knobs to let you change that behavior.
Right. Yeah. Okay.
And I want to mention one other thing, and I'm sorry, but like I said, it's a big improvement. It's a big language.
Yeah.
Because again, getting back to R-value references, what I said was that there's two higher level features that R-value references help implement. The most important one, I think, for most people will be what's known as move semantics.
Yep.
But I want to mention just in passing, the other one is what's known as perfect forwarding. This is a feature which is really only going to be of interest to library developers. But one of the challenges which has existed in C++ is that if you wanted to write a template that essentially act as a wrapper, then what you really wanted to say was whatever parameters are passed to this template, I want to turn around and pass them exactly the way that I got them to some other template. This is what's known as the forwarding problem.
Yeah.
It turned out that there were some technical issues where you could not perfectly forward what you got.
What does it mean to perfectly forward?
Perfectly forward means that, one of the things in C++ OX that is more important than it has been in the past is the difference between L values and R values. And an L value essentially is an object whose lifetime is being controlled by the user. And squint, then an R value is an object whose lifetime is controlled by the compiler.
Yep.
And it turns out that this distinguishing between L values and R values is actually what makes move semantics work. Because the compiler knows what's an L value and the compiler knows what's an R value. And because it knows that, it can figure out when a move is valid and when it's not. So what this means is when you're writing a wrapper function, what you want to be able to do is if somebody passed you an R value, it's very important that you forward it as an R value. But if somebody passed you an L value, it's very important that you pass it as an L value. And when you get a parameter has a name, and that means that the programmer controls the lifetime of that parameter.
Yeah.
They can decide when to use it and when not to use it. But the problem is if it was passed in originally as an R value, then because it's now a parameter and it has a name, now it's an L value. And you have to have some way of magically turning it back into an R value. And perfect forwarding is the name that we give for the mechanism that is used to make that possible.
I see. Okay.
And again, the underlying implementation mechanism is based on this new language feature called R-value references.
Okay. I guess if I really need to understand the details, I really have to take a look at some code, I guess. But and I think that's
well, but again, the nice thing is at a very high level, move semantics simply means that things will be more efficient without you necessarily doing anything about it. And perfect forwarding means that as a library writer, you're going to be able to do things seamlessly that you could not do before.
Okay. The next one, variadic, if I pronounced that correctly, templates. What's that?
Yeah. Variadic templates means you can write a template that takes any number of parameters of any type and manipulate them in a type-safe fashion. So up to this point in C++, before C++ OX, you might say I have a template function that takes 5 arguments. But there was no way to say I have a template function that takes n arguments.
It's like var args in Java, kind of?
I don't know about Java, but it's like var args in C, except it's type safe.
Okay. Yeah.
So you basically never lose the type information.
Yep.
So what it means is now you can write templates that don't care how many types are passed in, but can manipulate them in a type safe fashion.
Okay, so you kind of say this function takes basically an unlimited list of arguments of type T.
No, you say this function takes an unlimited list of arguments of any combination of types. They don't all have to be of type T.
Ah, okay.
Remember I talked earlier about the async function?
Yeah.
I said you can pass that anything that is executable,
yep,
along with any collection of arguments of any type.
Yep.
Variadic templates are how you do that.
I see. But then, if I write the implementation of that function, how do I know how to treat each of these things? How do I find out what the types are? I mean, how can I do anything sensible, or can I just forward them or do something generic?
Well, again, it'd be a lot easier if I could show you code. But effectively, what you do is what you receive as an implementer is you essentially receive a type-safe list of everything that was passed in, and then using certain programming techniques, you essentially walk down that list. And so you say, okay, the first one is of this type, let me do this with it. The second one is of this type, let me do this with it.
So you need some kind of runtime type information going on there.
No, it's all done during compilation. This is still C++.
Okay.
Remember, the compiler knows what the types are.
Okay. Let me rephrase. You need some compile time reflection capability.
Let me put it this way. If I want to, let's suppose I want to print out some object of type T. Then usually what we've done is we've overloaded the output operator.
Yeah.
So that whatever T is, it prints in the appropriate way.
Yep.
So if it's an int, it prints like an int, and if it's a string, it prints like a string. So the way we do that is through overloading.
Yep.
So you never had to say, well, is this an int or is this a string? You simply let the compiler go, oh, this is an int. Let me call the appropriate output operator for an int.
Yep.
So variadic templates essentially do the same thing. So you'll get some parameter. It happens to be of some type T. You don't know what it is, and you're virtually never going to query what its type is. What you're going to do instead is you're going to invoke some operation on it.
Yeah, okay.
Now, whatever operation you invoke is probably overloaded, which means the compiler is going to automatically figure out the right one to call.
Yep. I see. Okay. The usual approach in that way.
Yeah, in other words, it simply dovetails really nicely with overloading on types.
Yeah. Okay. The next one I wrote down is Lambda Functions. Now, this sounds a bit functional, so it seems like C++ is going a little bit in the functional direction.
I guess you can think of it that way. Lambda functions are simply unnamed functions that you create. Actually, to be quite precise, they're unnamed function objects that you create on the fly at the point where you need a statement. And I think now exist in C#. And does Java have Lambda functions as well?
Well,
no.
This whole story about implementing closures, which is kind of the same thing as Lambda functions, more or less, is a sad story. I have lost track about in which standards they're going to. Perhaps, I don't know. It will come perhaps at some point. I'm not up to date.
Yeah. Well, anyway, so Lambda functions are unnamed function objects that you can create pretty much any place a statement is necessary. And they're extremely convenient in two cases. One of the cases where they're very, very convenient is when you're actually spawning off a separate thread of control.
Yeah.
So, for example, let's suppose you want to you want to say you want to compute f plus g and get the answer, but you want that to be done asynchronously.
Yep.
So the really nice thing is you can call async. You create a Lambda function. The Lambda function has no name. You simply say, I want to add f and g together, and async says, great, I will create a function object for you. Here's the future. You can now go off and do your thing.
Yeah.
So one really nice place to use Lambda functions is when you're doing threading.
Is there a special syntax then to write those lambdas down, or do I have to do some, let's say, weird class thing?
No, there's a special syntax. It turns out that when you write a Lambda function, it looks a lot like a regular function. But what actually happens is the compiler automatically generates a class for you, sets up the appropriate data members, and then does the appropriate stuff.
Okay.
It saves you the trouble of writing a class.
Yeah.
And the other place where Lambda functions are very convenient is when you are doing things in the standard template library.
Yeah.
So if you wanted to be able to say things, for example, I have a collection, I have a vector of widgets, and every widget has, an age. And I've decided that what I want to do is I want to sort this vector of widgets in decreasing order based on their age.
Yeah.
And that means I need to have some kind of a special comparison function which will compare two widgets and return which one is older. And a Lambda function is perfect for that.
Yeah.
Because you don't want to write a separate class. You don't want to write a separate function and put it someplace else. You just want to say, sort it based on this criterion. And the Lambda function is an economical, terse way of expressing what you want to do.
I guess that's the important thing, because something people might forget or might not know is that you could write what you'd like to maybe want to call higher order functions. You could always write them in C or C++, I should say, by using function objects, right? But the syntax was kind of ugly. And now, so these Lambda functions, or they just basically they provide a syntactic abbreviation for building a function object, right?
Exactly.
Okay. Mm-hmm.
Yep. And they're very convenient.
Yep. I understand. That's Java needs this urgently. I mean, except that by the time that Java has it, I guess everybody uses Scala, which does a nice job of these things. At least that's my strategy. So the last language feature that I wrote down before we're going to take a look at the library is the uniform initialization syntax and initializer lists. What's that?
It's two separate things. One of them is uniform initialization. It just turns out that from C, as well as some stuff in C++, there are a lot of different ways to initialize things, a lot of different syntaxes. So even in C, for example, you could say int a equals 5. Mm-hmm. But you could also, for example, if you had an array of int, then you would say equals, and then you have an open curly brace and a list of values.
Yep.
In C++, we then added constructors. So now you could say things like, widget w open paren a comma b comma c.
Yep.
So already we have three syntaxes. We have the equal sign to initialize the int. We have the curly brace list for initializing the array. And we have the parentheses for initializing the object which calls a constructor.
Mm-hmm.
So we have three different syntaxes. And when you start writing templates, this becomes very problematic because you don't necessarily know what syntax to use to initialize whatever your object of type T is.
Yeah.
So uniform initialization essentially says we're going to let you use braces virtually everywhere.
Okay.
So you can initialize an int using braces, you can initialize an object using braces, you can initialize an array using braces, and so it's called uniform initialization syntax because the syntax for initialization is now basically the same everywhere.
So I could write int I, and then instead of equals 5, I could opening curly 5 closing curly.
Exactly. The equals will continue to work, but the new thing. The new thing is that the braces will work.
Okay.
And furthermore, they will work not just with built-in types like int, they will also work with user-defined types like, tree or customer or whatever you want it to be.
Nice. Okay, that's a good way to kind of write down structure literals, if you will.
Yeah, and so once you started doing this, so that's kind of step one of uniform initialization. Well, the thing is now, let us suppose that you have a user-defined type. And the user-defined type, let's suppose that it's it's a point, and so you want to have an x value and a y value.
Yeah.
And I guess we're very fancy these days. You can have a z value as well. So you've got an x, a y, and a z. But let's suppose you'd also like to have some kind of a list of weighting factors that should be applied to this point when it's used in certain contexts.
Mm-hmm.
So your data members you have, let's say, an int x, an int y, and an int z. But you also have, let's say, a vector of weighting factors.
Mm-hmm.
And what that means is when you're calling the constructor, what you want to pass in is the value for x, the value for y, the value for z. But then you also want to pass in an arbitrary number of objects that are supposed to go into that vector.
Yep.
And so now there is a new thing in the standard library called an initializer list. And an initializer list is basically a collection of values that are enclosed in braces, which can be treated as a single thing.
So it's like a list literal.
It is like a list literal, yeah.
Okay.
But the nice thing is now remember we already have variadic templates, so we can pass in as many arguments as we want of as many type as we want.
Mm-hmm.
This allows us to say I've only got one argument, but it has multiple values. It's sort of like passing in you're right, a list literal.
Yeah.
So and it works with the same syntax as uniform initialization.
Mm-hmm. Okay. Nice.
I've actually played around with these features because they're in some compilers, and I have to tell you that when you sit down and start writing little toy programs playing around with these new features, you just can't help but have this big grin break out on your face. Things just so nicely. It's really very sweet.
Yeah. Okay, before we go on to the library, there is one thing that I think I heard about the OX standard at some point, and I think it was called concepts. Is that am I wrong, or is it still in there? Has it been deleted? What's the status?
You're not wrong. Concepts were for a long time going to be the big new marquee feature for C++ OX.
Yeah, exactly. Yeah.
And last summer, they were removed from the draft for C++ OX because the standardization committee as a whole was not able to agree on some important details of their specification.
Okay.
And so concepts got removed. And,
is it worth discussing in 1 or 2 minutes what they would have been?
Concepts effectively were supposed to make it possible. Let me put it this way. In Java, you have interfaces. And so you might say, I'm going to write a generic, and the generic has to support interfaces A, B, and C.
Mm-hmm.
Correct?
Yeah, you can write a class that's generified, and it can implement A, B, and C. And the other way you can do it, you can say the type, the generic parameter of some class has to be a subtype of the following combination of other types. Yeah.
In other words, in Java, you can say, I'm going to take some type T, but T has to implement the following interface.
Yes.
Right? Okay, in C++, there's no way to say that. There's no direct way to say that.
Mm-hmm.
And furthermore, it turns out that that's not exactly what we want to be able to say in C++ most of the time. What you'd like to be able to say in C++, for example, is that I'm writing a template, it takes an object of type T, and T has to support, let's say, the plus operation.
I see.
T has to support, let's say, the copy operation. And maybe T has to support the clone operation.
Yeah. In Scala, that's known as structural types.
Okay. So the idea behind concepts was to give you a syntax as a template author that would allow you to specify what these constraints on the type T are.
Okay.
Okay, that was the idea behind concepts, and it was the motivation was, number one, you'd be able to give much better error messages if it turns out that your types didn't support the right sets of operations.
Yep.
And then it also made life easier for library implementers in implementing certain kinds of things.
Yeah.
So that was the motivation behind concepts, and they did a tremendous amount of work on concepts. But like I said, last summer, so about 9 months ago, I think it was last July, the standardization committee decided that they were not going to be able to reach consensus on some very important technical issues related to concepts. And rather than have that issue keep C++ OX from moving forward, they simply decided to remove concepts from this version of the language.
Mm-hmm. But with the idea of potentially adding it in 25 years to the next C++ standard.
Yeah, I think that probably the operative word there is potentially.
Yeah.
My sense is that the drive for concepts lost a lot of steam, but we'll see what happens.
Okay. So let's take a look at the new features in the standard library. The standard library obviously plays an important, especially the container library, I guess, plays an important part in the C++ world. And so what new stuff do we have there? I guess there must be some stuff for concurrency, right?
Yeah, it turns out most of the concurrency stuff is actually in the library.
Right. Yeah.
So, for example, Promise is a class in the standard library. Future is actually more than one class in the standard library. Mutex is a class in the standard library. And I should actually mention that most of these things, when I call them classes, almost always they're actually class templates.
Yeah.
So almost everything in the standard library is a template. So a lot of the concurrency, async is a class template. Actually, async is a function template. So most of that stuff. It turns out there's also some very primitive support for doing expressions of time in the standard library, and the reason it's there is because we need to be able to specify timeouts on certain parts of the concurrency library. So if you want to try to acquire a mutex, for example, but you don't want to wait more than 10 milliseconds, you need to have a way to specify what 10 milliseconds is. So that's in the standard library. One of the things that has been proven to be very useful for C++ programmers is reference counting, because there's no garbage collection in the language. There's still no garbage collection in the language.
Yep.
But reference counting is what we use in many cases. Rather than having everybody re-implement their own version of reference counting, which aside from being tedious, turns out to be really very difficult to do in a thread-safe manner if you also want to be efficient. There's now a standard class a standard class template called shared pointer, which is a reference counting smart pointer, which automates reference counting, and it has something else associated with it called weak pointer, which just makes it easier to make cyclic structures and observers and stuff like that.
Since you mentioned garbage collection, you know this joke about C++ and garbage collection, right?
No, I'm probably not.
So there is this joke which says, why doesn't C++ have garbage collection? And the answer is because then nothing would be left. I'm surprised you didn't know it.
Curiously enough, that joke doesn't make the C++ circles.
Yes.
Now, I have to point out, because I take a certain solace in this, one of the things that C++ is supposed to be good for is very low-level, efficient programming. And so the last time I checked, if you look in the underlying implementation of the runtime system of the CLR for .NET, the underlying CLR is written in C++.
Sure.
And last I heard, the hotspot compiler for Java, the core of that is also written in C++.
Sure. And I guess, I mean, to me, it wouldn't make any sense to add garbage collection to C++ exactly for the reasons you just outlined. I mean, this is a different focus. It's a different kind of language. Otherwise, it would become Java, and we already have Java. So what's the point?
Well, for what it's worth, actually, C++ OX for a while was going to have some support for garbage collection. There was going to be actual optional garbage collection in C++ OX.
Oh, okay.
But that got eliminated along the way.
Yeah, not surprised. Okay, I think regular expressions are now also in C++ in the standard library, right?
Yeah. Now, I mentioned earlier that in 2005 there was something called TR1, which was a collection of 14 libraries. So those have been available in one form or another since 2005. Most of the new standard library stuff that we're going to talk about right now is essentially C++ OX versions of what was in TR1. Okay. So regular expressions are one of those things. So we've had, in some sense, regular expressions since 2005. We just have slightly better regular expressions now. And one of the things that makes them a little bit better, for example, is we now have what are known as raw string literals in C++ OX.
Oh, okay.
So you specify a string literal that looks like a regular expression without having to put a backslash in front of all the backslashes.
Yeah. Makes sense.
So yes, you've got regular expression searching, and you've got regular expression replacing, and regular expression matching, and it's very powerful. It's pretty much what you'd expect from a regular expression library. And this being C++, it's all templatized, so it works on any arbitrary types that can be considered strings of symbols.
Ah, okay, cool. So you can build your own kind of, let's say, matching facilities for your own structured data.
Well, the matching algorithms are built in, but for example, if you want to do it over you can pass in, for example, two iterators. So it doesn't actually care it doesn't care whether it's matching char stars or long char stars or Unicode char stars or your own custom string type. In other words, it's not limited to a particular collection of types.
Okay.
So if you have a type that looks like it's a sequence of characters, you can use all of the regular expression machinery on that.
Okay. Generalized functors and binders. I have no idea what I should make of that, so I guess you have to explain.
I mentioned earlier. Well, this will be a generalized functor is a generalization of a function pointer.
Okay. So that's this thing that you basically can pass into async, right?
Well, async is more general than that.
Okay. Okay, I tried.
Well, I mean, there's a lot of this generalization stuff. Essentially, let me put it this way: in the same way that async will take anything that's callable, in some cases, what you want to say is, I need a variable, or often it's a parameter. You often want to say, I need a parameter that can hold anything that is callable.
Yeah.
And that's what a generalized functor is. So it can point to a function. It can be a function pointer, but it can also point to a function object.
Yeah. Okay. I see. So it's kind of the opposite. I mean, if you can pass around functions, you should have something that can hold these things.
If you pass around things that act like functions.
Okay.
So they might be functions, but they might actually just be objects that act like functions.
Yeah. Okay.
And a binder you've talked before about, for example, if you have a method and if you pass a method around. In general, in C++, when we are manipulating functions, we treat them as non-member functions syntactically. And what that means is if I have a method, I have to also have an object on which to invoke that method.
Yep.
So I know which object the method should be invoked on, and then you pass additional parameters. And so a generalized binder, among other things, allows you to say, okay, this is a method, and this is the object I want to invoke it on. Let me bind the two of them together, and now I can pass that around as a function.
Okay. Mm-hmm.
But it also turns out that it allows you to say, I have a regular function or a function object. Let's suppose it takes 3 arguments. And I happen to know at a particular point in my program, I'm doing some calculation, and at a particular point in my program, I know that the second argument is going to have some value. But I haven't figured out what the values of the first and the third arguments are yet.
Yeah.
I can bind that second argument value to the function and thus create a brand new function object which only takes 2 arguments.
So that's currying.
It is exactly currying.
Cool. Nice.
Exactly currying. Mm-hmm.
It's interesting. I mean, there's quite a lot of stuff coming. I didn't expect that. I mean, from good old C++.
Yeah, no, there's actually a lot of really interesting stuff in C++ OX.
Mm-hmm.
Mm-hmm.
Okay.
And I'll also mention that both of these things, functors, generalized functors and generalized binders, those again are derivatives of what was specified in TR1. So they've been around since 2005.
Okay. Well, I didn't notice.
Well, if you weren't programming in C++, there would have been no reason to.
Yep. Hash tables, there's also something new about them. I'm surprised. Haven't there always been map kind of structures in the standard library? There
have always been maps and sets, but those were balanced binary search trees. So they were always...
Okay.
The hash tables are just what they say. They're actual hash tables that fit into the structure of the standard template library.
Yep.
It's something that everybody wanted, and in fact, they would have liked to have them in 1998. It just turned out that it would have been too much work to nail down the specification.
Okay.
So again, they're something which were specified in TR1.
Okay, but there is no literal syntax for map entries, except that you can, of course, always, pass in some kind of templated tuple kind of thing. But there is no special syntax for hash literals.
What do you mean by a hash literal?
Like, for example, Scala has it. You can basically write something like, so if you have a hash map and you want to initialize it, you can pass in comma-separated lists of values which basically look like, key, arrow, this rocket symbol equals greater, and then the value. So the hash literal is a name-value pair literal with a special syntax.
Okay, you can achieve the same effect thanks to uniform initialization and initializer lists.
Mm-hmm.
So
and maybe go ahead.
So in other words, if what you want to say is I have a hash table and I want it to have the following keys and the following values,
yep,
you can do that using uniform initialization. You just use braces.
But you would pass in the keys and values separately and not a set of key value pairs and a list of those.
Well, you'd actually put each key value pair together inside their own set of braces.
Oh, okay.
So,
okay, I get it. But it looks like it would be this syntactically. It would be the same as if it were a vector of pairs. I mean, there is no special syntax for the fact that it's a hash map, but you don't need that anyway. So
let me put it this way: the goal of C++ OX would have been to say you shouldn't have a special syntax for that.
I agree.
Instead, you should use the same syntax you use for any other container.
Yeah. Okay.
Which is the same syntax you use for any other variable.
Yeah, makes sense.
That's the whole idea behind uniform initialization syntax.
Yeah. Okay, the last thing I had here was tuples. There is some support for tuples too, I guess.
Yes. So, I mean, C++ has always had support for pairs, which is, two things of arbitrary type. So a tuple is simply an extension of that to an arbitrary number of components.
And is that done... The way it's done in Scala, I think, is that there is 23 classes, tuple 2, tuple 3, tuple 4, tuple 5, up till tuple 22, I think. Is it done the same way, or is there some more template magic, var args, variadic stuff going on?
Thanks to variadic templates, you only have to write one. You write one template, and you say it takes an arbitrary number of objects of an arbitrary number of types, and it just works.
Nice.
Mm-hmm. So and as a result, there's no. You don't have to impose a limit of you can't have more than 23 different components of a tuple.
Well, but I guess as soon as somebody has a tuple 23, I guess there is some refactoring potential. Anyway,
Well, I just want to mention in passing, because it is important in practice. It is not uncommon for people to have code that is generated by machine rather than by humans. And when you have machines writing code, that it's not uncommon, for example, to have functions which take 100 parameters. No human would do that, but a machine might. And so it's not, in my experience, it is not uncommon to have machine-generated code look like really awful human-written code.
Well,
and I think it's the language to support that.
I spent almost all my professional time building domain-specific languages and code generators. Mm-hmm. And if a customer, with whom I'd work, wrote a generator that would generate that kind of code, I would say, why don't you write a generator that generates readable code? But that's another story.
Yeah, which would be fair enough.
Yeah. Okay, so anything else? Anything we missed? Any additional thing that just came to your mind that you kind of want to mention about? Because otherwise, I think we're kind of through.
I'm just going to all I'm going to say is that we have not talked by any means about everything that is in C++ OX, and we've certainly hit the high points. But as I said, when I first sat down and looked at it, I sort of thought there's going to be a few new features, but there's a whole ton of stuff.
Yeah.
There's a lot more control over exactly when the compiler generates certain kinds of functions and what they do. And so, we've talked about most of the things, but we haven't talked about everything by any means.
So during the preparation, the little that I did for this episode, I Googled a little bit, and I found, among other things, a really nice Wikipedia page about the new features. And I thought it was obviously probably wasn't complete, but it was understandable and readable. So I guess I'll put that into the show notes. Do you have any other suggestions where people can find further information about this stuff?
I'll send you a couple of links. One of the things that I did want to mention is a lot of these features exist in at least one compiler now.
Yeah.
And so, like when I talk about, it's really fun to play with these things, I'm actually talking about writing programs that will compile and that will do something. So there's actual experience that we have with these things. So I'll send you a link to a page that I've put together, which summarizes for Visual C++ and also for GCC which features they support, but it also has some links to another Wikipedia page that shows a couple of other summaries of which compilers support these features. Mm-hmm. Because I do think it's important for people to understand this is not a theoretical language thing, and we have to wait until 2011 to use it. You can start using a lot of it right now, and it's something I definitely encourage people to play around with, because it's a very sweet language to program in.
Mm-hmm. Very nice. And in the worst case, if they don't get it, you'll probably, they can probably convince you to sell, some consulting or training. If it really, if it's really necessary.
There's a lot of stuff there. It's like anything else. The easy features are pretty clear and straightforward. When it gets down to, for example, writing the code to walk the list of variadic templates and do something with each parameter, it's not hard to do once you know how to do it, but learning how to do it takes a little bit of time.
Yeah. Okay, then, Scott, I guess I thank you very much for being on the show. I thought this was a very good, very interesting episode. And, thank you.
Well, thank you very much for having me. I appreciate it.
Good, great. Bye.
All right, bye-bye.
Thanks for listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig Reddit Delicious links and the /dot button. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the Podsive Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.